This video is about Chapter 7-1, Woodstoves and Heat. And I couldn't do better than to introduce you to my father. That's him right here. And he built this log cabin that you see behind him. You can see there's a picture of my husband and I on the wall right there. My father was actually told he would be lucky to get out of bed. He would be an invalid for the rest of his life after he hurt his back. Well, guess what? He didn't pay attention to them. Instead, he developed his own physical regime to help heal his back because he was a veterinarian. He knew how to do these kinds of things. Completely ignored the doctor's advice and essentially cured himself, and not only got out of bed but built this log cabin, actually this whole big log cabin and a whole slew of other log cabins. And he felled the trees himself, put the logs together, built the structures, and inside this log cabin was the most gorgeous old stove that you've ever seen. It was very much along the lines of this one on the lower right. A beautiful old wooden stove. So we used to dump a bunch of wood in there, and this whole stove would radiate this wonderful warm heat. How did that heat come out and reach us? What are we really feeling, in fact, when we do feel heat? As it turns out, and I've mentioned this a little bit before, when we feel heat is actually mostly just the motion of molecules. In some sense, it's both kinetic energy, Ke, kinetic energy, and potential energy, because the motion of two molecules, for example, that are somewhat attached to one another, they're attracted. What they can do is they can bounce back and forth together. They're attracted and repelled, and they vibrate, and this motion is actually part of what we feel as heat. In fact, at a very, very deep molecular level, molecules have a strong repulsion if you get them too close together, and a weak attraction as they get further apart. So this is an attempt to illustrate that idea of molecules have a certain point where they'd like to rest together, right? They'd like to sit together. And you know what? The best thing for me to do is to show you an animation. Here we go. This animation or simulation shows two neon atoms, and they're fairly close to one another. What happens if I move one of them just a little bit? Okay, well, look at here. This is the potential energy. Oh, look at that. See, it wants to go to this lowest point where it reduces its potential energy as much as possible. That's like falling to the bottom of a hill. But as it goes to fall to the bottom of the hill, it overshoots a little bit. And as it gets too close to the other molecule, it actually is repulsed by it, because as it gets very close, there's this repulsive force. So what happens is it bounces between this repulsion as it gets very close and an attraction as it's further away. Let's see what happens when we go to two different types of molecule or atoms, argon and argon. Slightly different. Notice they're a little bit further away from one another. And again, it bobbles back and forth between the attraction and the repulsion. Let's see what happens if we take it way out. See, a weak attraction. Closer it gets, the more it's attracted. Look at that. Bobbles back and forth, depending on how far away we get, of course. So heat, a big part of heat is this vibrational back and forth that goes on with in between the as it's repulsed alternately and attracted. Let's try oxygen and oxygen. This one is kind of cool. Okay, watch this. take it a little bit away. Oh, it goes crazy. It can't quite get onto that exact fit, so it bobbles back and forth. Let's go to neon and argon, because we want to put those little oxygens out of their misery. You can see different distance apart, but the same essential idea. The hotter a molecule can get, the more it may rotate and swivel around, also bobble back and forth, vibrate back and forth faster and faster, and also it can have different vibrational modes as well. So that gives a good sense there. Now I just want to remind you a little bit of some basic chemistry ideas. Remember that the different elements in chemistry are made up of protons, neutrons, and electrons. So I've just made a hydrogen ion. I can add an electron if I want to. There's a neutral atom now. I can take, let's see what happens if I add in neutron. Okay, now watch, proton. Okay, now I've just made helium. Let's see if I can take away this. Oh, now it's unstable without that neutron, so we're going to put that back in there. Now, here we go. I'm going to add this. Notice how that electron traveled to the other side. It's if I already have an electron in place, it can only have the second electron in another place. That's actually fudging a little bit. If I showed this as the electron cloud, it would look a little bit different. Let's show you here. So I am fudging a little bit because the cloud, electrons are actually somewhat statistical in nature, or actually quite statistical. Okay, so here let's put some more protons on it. Now I've just made a lithium. It's unstable, poor little thing. There's beryllium and a boron. Let's add some neutrons so we can stabilize things. Okay, come on, get back here. Okay, now it's stable. Now watch what happens when I add an electron. Okay, I'm going to try and put the electron right up here in the nucleus. It didn't want to go there. It goes to a second outer orbital. Okay, let's put this. So this just kind of reminds you of what atoms are doing when they're being created, or what the differences are between some of the different atoms. And we'll stop back by and visit our neon-argon relationship, and look, it's still bobbling back and forth, back and forth. So let's summarize here. When we have thermal energy, it's just jiggling molecules, and that means we've got kinetic energy, movement, and we've got potential energy, which is the molecules are pushing and pulling on one another. So notice that's a sort of movement too, but it's sort of like pushing on a spring. So that is a movement, but once you've got the movement, the spring is compressed in some sense. You've got some potential energy that's stored within there. For wood stoves, or no, I should say for wood, it's the wood's atoms and molecules that are moving, right, and that are having this potential energy. And but there is something different, and that is for metal, we've got the atoms and the molecules, but we've also got the electrons. If part of thermal energy is kinetic energy, then you saw we may have an atom. It's got its nucleus, protons, and some neutrons. Okay, it's got electrons going around the outside. Those electrons actually make motion as well. And it turns out that in the lattice of metal atoms, say copper, something like that. So let's say you have a layer of copper on the bottom of your pan. There's the electrons in metal, they don't just stay around one atom. They actually kind of can float anywhere in this metal. They can travel around from being passed around from molecule or from atom to atom. So the electrons form kind of a cloud, and they can carry, just by virtue of the fact that they are moving themselves and moving sometimes with quite a bit of energy, they carry that that heat energy with them in their motion. So what is a burning log? As it turns out, it's just a huge assembly of atoms and molecules that are held together by chemical bonds of various strengths. These particles push and pull on one another as they vibrate around their equilibrium positions. Their motion is thermal motion, and the energy involved in this disorderly juggling is thermal energy. Because thermal energy is fragmented among the atoms and exchanged between them unpredictably, it can't be used directly to do work. So you might ask yourself, what exactly is temperature? Well, it's just the quantity that indicates which way, if any, thermal energy will naturally flow between two objects. So temperature is sort of a common sense relative way of thinking about the quantity of how hot something is. Heat is just energy that flows from one object to another because of a difference in temperature. So heat, then, is thermal energy on the move. The Celsius, Fahrenheit, and Kelvin scales all measure temperature by measuring an object's average thermal kinetic energy per atom. So in each scale, a 1 degree or a 1 unit increase in temperature reflects a specific increase in the average thermal kinetic energy per atom. These relationships are based on several standard conditions: absolute zero, water's freezing temperature, and the boiling temperature of water. Now your book asks, if you pick up an ice cube, your hand suddenly feels cold. Which way is the heat flowing? That's really quite similar to this situation with a little boy just about to put his tongue on a very, very cold metal pole. If his tongue did touch that pole, and let's hope that it didn't, you know that the tongue would be hot and this pole is ice cold. Do you think that the cold flows into the tongue? No, of course not. Heat always, always, always flows from hot to cold. So it may feel as if the cold has flowed in there somehow into the tongue, but that's not what's actually happened. What's actually happened is simply that the vibrational and all that little tiny kinetic energy from heat here has started to flow out. And so it feels cold because the heat has flowed from the hot area to the cold area. Okay, let's try and get a little bit better handle on combustion. First, let's go back and look again at our two intertwined molecules or atoms. They want to hang out together. Remember, they're alternately, when they get too close, they're repulsed, but they're also attracted, and they want to hang out at this lowest energy level. So that's exactly what this neon and argon are doing. They're trying their best to get as close as they can. They kind of bobble around there, but they go to this low energy level. Well, as it turns out, wood is, let's get our pen back here. Wood is mostly cellulose. That's a carbohydrate. And what it's got in it is basically carbon and hydrogen. Oops, hydrogen. There's a little oxygen in there too, but not very much, so we won't worry about it. So the carbon molecules and the hydrogen atoms, they want to hang out together, and they do so as hydrocarbons. Right? It's a long chain. Basically, it's just a molecule which is at its lowest energy level when the carbon and the hydrogens can all rest pretty darn close to one another. It turns out, however, that if we could take that carbon off, if we could take the carbon and we could rip it off and let it hook together instead with some oxygen. So it made CO2 on the one hand. Carbon dioxide is what that is. Carbon dioxide. And then on the other hand, well, look, we've got this hydrogen left here. What if we let the hydrogen go run off with some more oxygen? Well, we know what hydrogen and oxygen makes. That's just water. Right? If we could rip off the carbon, let it go run away and play with oxygen, and we could rip off the hydrogen, which is connected here, and let it go run off and play with oxygen, we could actually it turns out that each one of those new combinations would actually end up being at a lower energy level than this previous hydrocarbon. The catch is, how can we rip these guys apart to let them fall into an even lower energy level? To do that, we need an activation energy. And that's often provided by a simple spark, a match, a light. That gives us enough sort of starting energy to be able to break apart this hydrocarbon and allow it to fall together with other atoms and molecules to result in something that's an even lower energy level. But wait a minute, if it falls down to a lower energy level, what happens to the energy that it gives off? That energy, as it turns out, is heat. That's the energy it gives off. So that's why when we're sitting in front of that burning wood stove, we feel some heat. But there's sort of a trick to it. For us to feel that heat, it has to propagate out to us. Let's look here at this modern furnace. So over here we've got this modern furnace which burns natural gas. It's got an S-shaped firebox. See the S shape right there? And there's a fan, a big kind of a squirrel cage fan at the very bottom. And what that does is that helps blow fresh air past these S-shaped fireboxes, and it blows the hot air through the house. So this combustion, this hot gas itself does not pass through the house, and in fact you don't want it to go through the house. Instead, the hot air blows past this warm area, or rather the air blows past this hot area and is itself warmed, and that's how your house is warmed. So the blower blows through here, heats the air, and then that's passed through the house. But I've actually given you a little bit of a glib lip service sort of thing. What I want to do now is tell you the 3 principal methods by which heat flows into a room. Or actually, heat flows in general. The first one is conduction. The second is convection. And the final one is radiation. So what is conduction? Conduction, first off, let's just think of my a pot that I'm putting on the stove, and you know there's metal around the pot, and I put a fire down here. There's my candle, and I've got some water. Let's make blue water. There we go. Here's my blue water. But what I'm interested in is how does the heat get through the metal into the water? To understand that, I'm going to give a close-up. Here's my metal strip right there. There's the bottom of the pot. Now, we know that it has, let's say, some atoms of aluminum. Okay, so we got some aluminum atoms there. And around the aluminum, we can have kind of running around are the electrons, right? And remember, the electrons can go wherever they want to. They can lope around freely. They don't have to hang around any atom in particular. Now, we have our flame. Okay, what that flame does, that heat, is that causes, see these individual atoms begin to vibrate more. Remember, it's just more motion. They're stuck in this lattice, so they kind of, this pushes over towards the next atom, which pushes over backwards. So they bobble back and forth. They're pushing and pulling on one another, and they do that more and more as more heat is added. At the same time, these electrons serve as sort of a bucket brigade, so they're carrying heat energy up here too. Now, on this side, we've got our water molecules. They come down, they hit this vibrating, it's actually, I show a smooth surface right there, but it really isn't. It's a bunch of vibrating molecules at a molecular level, right? So on the surface here, you've got this aluminum atoms here vibrating like crazy, and there's also some little electrons coming up, and they've got their own energy, right? And as this water molecule comes up and bumps against there, it captures some of that heat energy, and it starts, remember, it's got this sort of arrangement with hydrogens and oxygens, and it starts kind of bobbling, waving first in and then out. So it's vibrating a little bit because it's got some of that energy, and it might swirl around, right? Because it's rotating, it's vibrating, and it's translating. In other words, it's simply moving straight out. So it captures that kinetic energy from the surface of this metal, and that's what it's carrying off. But what's happening is that, see how it's almost like a domino effect. This first aluminum atom is hit, taps the next, and so conduction is when the molecules or atoms themselves do not move, but they allow this heat energy to flow through them. The electrons can move, and that's okay. That's still considered to be part of conduction. But the atoms themselves don't move. They just kind of, it's kind of like an ocean wave. The water molecules themselves don't really move, but the wave passes right over through them, just like dominoes. Okay, you got these dominoes all lined up. I can't draw very well, but push one, they fall. So the domino itself does not go very far, but the wave propagates very quickly through there. And that's exactly what's going on with conduction. So the best way for you to think of conduction, I'm going to erase all this, I hope that's okay. There we go, so I can draw right in the way there. I'm going to write down is that conduction is a measure, well, let's say, probably the best way is to say that atoms and molecules don't move, although the electrons can move, and the heat passes through. And we usually think of metals as having conduction. They're the best example. So now what's convection? Convection is something like, let's see, I'm sitting in a room, I'm all happy, right? And I'm reading away. Here's my book. And, okay, so I'm sitting on a nice chair there. And as I'm sitting here, air molecules come up and they bounce against me. And as they bounce against me, remember, I'm warmer than the rest of the room. They pick up some of that heat from me. And so then they go off. But the warmed up molecules actually tend to drift upwards. And they actually convect. In fact, have you ever noticed above a pan of hot water, something like that, heat will rise up above something hot, so that hot air will rise and cooler air will come in its place. Likewise, if you've got, here's the sea and here's the land, and the sun comes out, so some sun come out, and the land actually warms up quicker in the morning, so it starts warming up, and the air will begin rising over the land as this is warming up faster than the sea. So winds will sweep in from the sea to make up for the air that's moved upwards. So you'll have shoreward in the morning, and then at night it'll be actually the breezes will go the other way. Why? Because, well, at night the land gets colder than the sea, and so air will descend here and then it'll flow out this way as the air is rising out over at sea. But anyway, so the essential idea here is that with convection, the molecules move the thermal energy. And so it's like the entire molecule is moving. And a good example is simply warm air in a room. And also, room. Also, for example, if you're boiling water in a pan, okay, then the warm water on the bottom begins to rise to the top. That too is convection. Okay, now the last means by which heat can be transferred is radiation. At least this is according to your book. I'll talk about one more. Sneak that in a little later. Okay, before we do anything further, well, first I want to remind you that we've got a positive, a negative. There are electrical fields that go between positive and negative, and we're very familiar with that phenomenon. Now let's make our own electric field. If you just move an electron back and forth, it turns out that that accelerating electron can actually produce an electric field that propagates along, it travels along. So depending on, let's try oscillating. Let's just do it so that it's going at a set pace. It's moving back and forth. Do you see how it's making this electrical field that sometimes it's big in some places and then it gets small and then it goes the other way? That's a traveling electric field. That actually, well, you may not see it here, but there's an electric, and what happens is it alternates with a magnetic field going sort of 90 degrees out of phase. But we won't worry about that. That's the whole idea behind electromagnetic radiation. You're seeing it right now. It's propagating along, and it's doing it very slowly, in some sense. What's happening, if you take a look here, this is a sense of the entire electromagnetic span of radiation. So if it alternates very slowly, as with our radio station, here's an AM station. It only alternates at maybe, well, so it's got a wavelength of around a kilometer. What's a wavelength? That means between this, well, see how it's right here from where it's going to a max to a min. What's the distance between when it's at a maximum? It keeps wiggling so I can't get it. But see where it goes to a zero here, and when it's zero again at the same time, you measure that distance. Well, actually skip the first one. So it's all repeated. I'm going to draw a picture for you. So there we go. There's one wavelength. So one wavelength here, if it's a kilometer long, that's, or a little, maybe a little less than that, it's something like AM radio. Now it turns out that if you go over here, let's see, microwave, here's microwaves. So your typical microwave might have a wavelength between here and here that'd be something like, I don't know, maybe 5 inches. as it alternates between. So depending on what, you can't see pretty much any of this stuff, right, until you get to this place right here. And there it's bobbling back and forth really, really fast. It's actually in the nanometers, like 400 nanometers. So it's like much finer than a human hair, much, much, much finer. And that's how these electromagnetic waves are alternating back and forth. And we can see only within this regime right here. See, look at where the color is. That's the visible and visible light. And this gives you kind of a close-up of that visible ultraviolet, or a visible light right in here. It starts at red, goes to violet. Down here you have this electromagnetic radiation, and it's below what we can actually see. But it turns out that like rattlesnakes can see in infrared, and they can see heat, because remember, I'm saying that radiation is one of the three principal methods that heat flows. So that's how rattlesnakes can benefit, is they can see the infrared radiation that is put out by bunny rabbits, for example, by virtue of the fact that they are warmer than their surrounding environment, and so they emit this infrared radiation. In fact, every object emits some sort of radiation based on what temperature it's at. So the sun emits electromagnetic radiation by virtue of the fact that it's super really, really hot. So that's why, let's say it's a really cold day, like icy cold, and it's maybe in the teens, and you walk out to your car, and your car has windows in it, and you go to get in, and let's say it's a very sunny day. It's very sunny, but very cold. You go to get in your car, and inside your car, have you ever experienced this? It's actually really warm. It's kind of warm in your car. That's because the electromagnetic radiation from the sun has entered in through your windows, warmed up the interior of your car, and that hasn't, if it's not windy, it stays warm, and the heat isn't conducted out through the glass or through the metal and carried away by convection if there's no wind. So it stays warm inside that car. When my husband and I used to be out in Antarctica, we would go out, and it would be like maybe minus 40 degrees Fahrenheit outside. And we'd set up a little tent, and it would be fairly translucent, and we'd go inside our little tent, and it would actually get up into maybe plus 30 or plus 40 degrees Fahrenheit. So an enormous difference in temperature, be quite warm in there. Why? Again, well, in Antarctica, during the summer, it has the radiant heat from the sun comes 24 hours a day. The sun never sets in Antarctica. So it would warm up, it would fall on the tent would be kind of translucent, warm up the inside of the tent, and it'd be quite cozy, even though the surrounding ambient air was very, very cold. So I can say that electromagnetic, or that radiation, in essence, electromagnetic radiation of all sorts. So this listing right here gives all sorts of different types of electromagnetic, and they just vary by differences in wavelengths. Some have a much longer wavelength than others. So light, radio waves, microwaves, ultraviolet, infrared, they all carry thermal energy in them. Oh yes, one ultraviolet. So ultraviolet is actually shorter wavelength than visible light, but some honeybees and birds can see in this ultraviolet regime. So some flowers have additional decorative decorations and so forth that occur, but you can only see them in ultraviolet light, so it's kind of cool. Let's take a quick look here. Let's say that this is my skin right here, the surface of my skin, that's on my arm. And I get a little bead of sweat. Okay, so a little bead of sweat comes out, sitting here. Here's water. It's a very hot day, and it's a dry day. So the water's sitting on the surface. Now, it's pretty hot. So what does that water have? We're going to magnify it. It's got a bunch of little water molecules. Now, this is water on the surface. And remember, water is just dead steam, right? So it can rise when it gets enough energy again. Every once in a while, one of these little rascals will get enough energy that it will rise up and leap the bonds of the surface of the water and fly away. When it leaps off like that, well, that took energy to do that, and that energy is heat. So evaporation carries away heat. Carries away heat by virtue of just jumping off into space. So our body, we've got some heat running around in our body, and it wants to. So our bodies have developed this mechanism where water will sweat, will perspire. The water forms on the surface, and then it can allow us to carry off some of that heat when the water evaporates. It actually can reduce your temperature by 15 degrees Fahrenheit. That water being able to jump off the surface of your skin can reduce the heat or the temperature of the surface of the skin by 15 degrees. That's a lot. So why do you feel so much hotter on a humid day? Because there's already a bunch of water molecules in the air. So there's sort of a water pressure that's already there. It's harder for these water molecules to jump up into the air. So it's harder to sweat, in some sense, on a very humid day. Whereas if you're out in the desert and it's very easy to sweat because your skin is so dry. Of course, you need a lot to drink because of that. But evaporation is what I like to think of as the fourth method of carrying away heat. And it carries away the heat because it carries away a lot of heat because it changes phase. Goes from liquid to gas. And obviously, if it's jumping up to become a very active gas, it's got to take a lot of energy off with it to do that. Okay, now finally, let's close in with warming the room. We're going to talk about two very closely related ideas. And that is, the first is heat capacity. And that's how much heat you have to add to cause the temperature to increase by 1 unit. Remember what I'd said earlier, something that's a very simple molecule like copper, it doesn't take much, you don't have to add much heat for it to increase in temperature by a unit. But something like water, which is much more complex, it has more ways to store the heat through its vibration, its rotation, it's all these kinds of things. That water, it takes a lot more energy in order to increase it by 1 unit. So essentially, what heat capacity is a measure of thermal sluggishness. Resistance to temperature change. So water is really pretty sluggish. That's why people who live near a large body of water, that usually makes the temperature so it's not so bad in winter, right? It doesn't get quite so cold, and in summer it usually doesn't get quite so hot because of the thermal sluggishness of the water that's nearby. So some materials warm faster, like land warms more quickly than the ocean. Others are more sluggish. So closely related to this is the idea of specific heat. Okay, so just like we have mass, we have density. This is the same sort of difference as between heat capacity and specific heat. So specific heat is how much heat capacity, if I knew how to spell, per unit mass. And so in essence you can say each material's specific heat depends principally on the number of microscopic ways it can store thermal energy per kilogram. So if you had something like a brass bowl, that would be just an empty brass bowl, that would be very quick to heat up. But if you had a brass bowl, so let's make a brass bowl, so that would be, put a flame on that, wow, it's going to heat up really fast. Now you put water in that brass bowl. Oh, now the water has a lot of ways to store energy. And so it has really quite a remarkable capacity for thermal energy. Now, one last little aside relates to one of my favorite objects in the world. I've got lots of favorite objects, as you're beginning to figure out by now, and that is my trusty rice cooker. How does a rice cooker work? It put your rice in. So you dump in your rice, and you put some water in with it. So the rice has water. Now, how does the rice cooker know to turn off automatically? That's the main thing about rice cookers, is you don't have to watch the rice to make sure it doesn't burn. It just turns itself off. Here's how it knows how to do that. It goes, okay, your water starts boiling and boiling, and you know as it's boiling, it's carrying away the heat. It's evaporating. So it keeps boiling, and the water level gets lower and lower and lower until finally the water is all gone. Okay, during the whole time the rice cooker is boiling, the water temperature is 100 degrees C. That's the boiling temperature of water. It doesn't get any hotter than that. So it keeps boiling away, and then it's all gone. What happens to the temperature of the metal that's containing that is the rice cooker? What happens to that temperature when the water all disappears? It starts to go up. It has no water to carry off that heat energy, and so it just starts to heat up itself. That's why you sometimes see this little brown spot on the bottom of the rice, on the rice cooker, because it started to heat up above 100 degrees C because all the water was gone. We have a little temperature detector there. It can detect that it goes above 100 degrees C, and it shuts off the rice cooker. So that is the miracle of how rice cookers work.
niggas in the crib, mom. Drop it like it's hot. Drop it like it's hot. Drop it like it's hot. When the pigs try to get at you, park it like it's hot. Park it like it's hot. Park it like it's hot. If a nigga get an attitude, park it like it's hot. Park it like it's hot. Park it like it's hot. Got the rum in my arm and I'm pouring Sean Don and I'm on the best weed 'cause I got it going on. I'm a gangster, but y'all knew that. The big boss dog, yeah, I had to do that.